Good day to all of you. Welcome to Connection Wednesday's webinar, a series of regular webinars delivered by Idea Statica. Today is Wednesday, October 17th, and we have another interesting webinar for you. Today we'll show you, or I myself will show you a import of a joint from SIA Engineer, a structural software, and that would be a steel tower structure. We'll get to that a bit later. First, let's introduce myself, Adam, a product engineer here at Idea Statica. And since my faithful colleague Jana is still on holidays, by the way, she's greeting you from Bosnia, I drafted another skilled colleague, Vít, to show us one example at the end as well. Just for some practical info, you are muted by default, but please feel free to ask any questions in the question panel. Just type it there and you'll get the answer during the webinar, or if we won't have enough time, just later by email. All right, so about the examples today, this is a shape of a joint that we'll be modeling together. Not completely from zero, as I said, it will be imported from SIA Engineer. So we'll see the whole process. And Vít at the end will comment on the one of the help desk highlights, quite a common question about the results or analysis of welds. He will show us tips and tricks and explain a little bit about some of the results and what does that mean about the graph and so on. So very useful tips at the end, so stay with us. And of course, as I mentioned, all questions please type in there and we'll try to answer them, or answer them loudly at the end, or just answer them later by email. All right, so let's jump to the example or the project that I'll show you live. It's a project of a steel broadcast or telecommunication tower. It's designed by an engineering office, Tecom CZ, which is one of the leading suppliers of telecommunication towers and masts. So they design or have designed till now a lot of projects all around Czech and surrounding countries, and mostly for telecommunication towers, but also for watchtowers, which is quite a phenomena in Czech Republic. We have a lot of lookout or watchtowers just for touristic pleasure and so on. So they designed this, and of course analyze, calculate, and then supervise the construction. So that's a Tecom CZ company, long-time user of Idea Statica, and they actually use Idea Statica together with SIA Engineer with the BIM-Link, and as they told us, that brought a huge effectivity into their workflow of the design process. So cut a lot of dead time or design time. So that was nice to hear that from them. And so the project is about this steel tower, which is actually anchored or attached to already existing building to a reinforced concrete wall, as you can see on the drawing here on the right. And here on the left, we have the detail of that joint that we'll be analyzing and code checking together in a minute. And so this is highlighted in the red circle where it lies. So yeah, that's about the project. It's now under construction. So let's check if it will stay in the place after it's completed. So I will jump to the SIA Engineer software, which I have here, and this is the project that we got from the customer. That's the steel tower model, a global model for global analysis of the internal forces. So how does that work with the BIM-Link with IDEA Statica? Since you install IDEA Statica on your computer, it integrates into your FEM and CAD softwares. So this is one of the FM softwares that we support with the BIM-Link, SIA Engineer, and that basically adds a menu or commands into the steel tab here, which I open now. And here we get the IDEA Statica connection menu. And here we have two commands. First one is to input a joint. So I will select one. I want to select the most complicated one here. Let me just turn off the 3D model so it's easier to work with. So I just select the joint and the members, click joint input. I will type here joint number 1. That's the name of that joint. Unselect that. Now I get this, let's say, flag here. That means the joint is selected for IDEA Statica analysis. And with the other command check, here I run the command and select the flag joint 1. And that makes actually the export to IDEA Statica, which is going to open in a second. Of course, that depends on the power of your computer. If it's 2 seconds or 10 seconds, as on mine. Okay, and we got the joint in here. So what we get, or what we can read from SIA Engineer, FEM software in general, is of course the geometry. So we can see all the cross sections are imported and all the members are in place, and also all the combinations. Yeah, so we've got 6 combinations here. As we can see, all is in equilibrium, all's fine. We've got many internal forces imported just by one click, so that's great news. So the last thing here we have to do is actually do the design. This is not yet automated. So let's do that, because actually it's kind of a pleasure to do that in IDEA Statica, right? It's kind of a game even that you play with the design of the joint. So let's start. I will start with connecting this bottom part. So just right click on the tube, connect it to the member. I select a weld, and here I will just manage the weld options. So there is no flanges, so I don't need any weld here. I will have one side fillet weld, and I will input the size of 4 millimeters. Good. Now I will do the same here for this one. And since I don't want to set these three things again, I will just simply copy this one and select this tube, which is now welded the same way. I will copy this cut command again, and now we'll select the main tube. Now they are welded together like this. Okay, so that's for the bottom part. That's done, and let's continue with the beam, the horizontal one. And here I will also weld this one to the main beam with this command. Again, I can just check here weld sizes. Let me see. This right-click command created two operations. One is cut, which is this weld here inside the main beam. I will also set the thicknesses of web and flanges weld for 4 millimeters. And the other command, another operation that was created by this right-click command is the weld. Is the butt weld, which we can see if I switch to transparent view. So it's the yellow line here at the top flange. There is no weld at the bottom flange because that right-click command is designed for smaller beams than for a smaller side beam than the main beam, let's say. So I will just copy this and put it for the bottom flange of the side beam and bottom flange of the main beam. Sorry, I made a mistake here. This is, of course, have to be this main beam 205. Yeah. So a yellow line in place. We have it welded all together. Okay. And now the top part, and this is not welded because it's another section of the tower, and that is not welded but bolted because by the means of the construction, of course, some of the parts are prepared in the workshop and then delivered on the site and bolted together and assembled and constructed. So this is exactly the place in the tower, in the construction, where this bolting is done. So what we will use for the operation connecting this continuing column will be the end plate operation. And I will choose the bolt assembly of 8.8 bolt grade and M16 bolt size. Yeah. And I will select the column. Here I select the main beam. I will select it automatically already. And of course, I will just modify the settings here. I'm fine with the thickness of 10 millimeters. I will make the end plate some bigger, so it's aligned with the top flange of the beam, like this. And of course, I need to place the bolts, which are now inside of here. I can show you that by unselecting the forces here so we get better visibility. Let me scroll down back to the operation settings. So let me change this to -10 and 30. So this looks much better, right? And again, I will just turn off the flanges weld and switch to one side, webs weld, and set 6 millimeters of thickness here because we have bigger forces acting on this column here. So we need a stronger weld. So I'll put 6 millimeters here. All right, another operation will be a stiffening plate that cuts through these two tubes. So let's create that. Select the operation stiffening plate. And again, modify the parameters. So the size, thickness of 10 is fine. And I will place it at the origin of a plate. And I will select the end plate, EP1. I will select it automatically because it's the only one in the model. So that was easy. And I will leave the rib type, location front. This is just exactly how I like it. So yeah, that's good. I will turn off the weld here. And now I will weld it together, these two plates, by a cutoff plate command. So let me do that. I will select this plate, will be cut by EP1 plate. Sorry, of course, EP1 plate is this one. Now just switch to double fillet weld and change the thickness to 4 millimeters. Good. This is all welded. Now let's cut this plate through the main column. For that, I will use cut operation, select column, switch to plate, select the plate, SP1, and switch to surface. Now the column got longer, and again, I can just change the thickness of the welds to 2 millimeters and turn off the flanges because it's just on the web of the tube. So now it's here and not inside, of course, because we have only the one side fillet weld. And the last thing, this tubular diagonal. So let's connect it. For that, I will just grab the first cut command and copy it and assign it to this one and to this one. So now it's cut like this. And now copy, switch to plate, assign it to the end plate one, weld is in position, and the last one will be, if I click on this weld, I will get the cut command, highlight it and select it, and I will just copy it and change to this tube. So again, it's welded here, and that's it. So I will now turn on the internal forces or the loads. We have the design done, and now we can calculate. So now by clicking the calculate, it will perform the analysis of all 6 combinations in a row. So that's going to take a minute, I guess. So in the meantime, let me show you, if you are interested in this BIM link, let's go to ideastatica.com webpage. We can go to resources. That's the resource center of Ideastatica. And if we select connection here, go to tutorials, BIM links, and here you have the tutorials step by step for all the softwares, well, almost all the softwares that we are linked to. So if you're interested in trying a BIM-Link with your software, if you haven't never done that, just please try this, because this is the future of designing process, right? So it cuts the time enormously, and we can see the SIA Engineer tutorial. If I open that, it takes a second because my computer is working hard. And here you can try this step by step. All is described: how to install the link, how to activate the link, how to use it, and the design of the joint to the end. Also, there is a chapter of how to update the project, which I'm going to show you as well in another webinar, because we're running out of time a bit. And of course, here at the top, you can download the project, the source files for SIA Engineer, which is this steel tower and the completed joint in IDEA Statica as well, so you can study that. Let me see. This is now done. This is calculated. So let's see just the overall look. All is green, orange weld, almost at the limit. So I passed the code checks. Design is good. It's actually quite efficient because I'm almost at the limit, but still on the safe side. So that's great. So I have safe and also economical design of this joint. So good. That's fine. So I can just save this now and close it. And now what it does, if I go back to SIA Engineer, it stays within the SIA project, right? So it stays inside the project file of SIA Engineer. So anytime I can go back, open the SIA Engineer project, and I can open again any of the joint that I have already designed and calculated. Everything stays there. So let me see, for example, I will open this one and show you one more trick how to save time. So I'll open this joint 4. Again, a few seconds. This is what I have already prepared in advance. I have designed the joint, I have calculated it. So let's revise, or let's take a look how it looks like. Okay, this is the shape. Again, we have 6 combinations imported, and there are just, in this case, just 4 operations, all is welded, a simple design. And we have all the results still here, so you can go back to this SIA Engineer project and reopen any of the joints, and you have all the information there, nothing is lost. And now the trick, so if you have let's say a structure where the shape of the joints repeat, like this tower, and you want to code check more of the joints with the same design, you don't have to design each joint by each, but you can use this template feature that we have here to help yourself. So I will create now a template of this one. Let's say SIA Engineer joint 4. template. Okay, now it's saved inside your IDEA Statica software, so that's fine. I will close this and I will select, let's say, for example, this one, and I will say, let's say, join 10. So there's the flag. I will open it, and that will be, of course, just a blank joint, just with geometry and internal forces. And because I want to rather have a coffee with my colleague than spending time on clicking all the operations and design, I will just apply the template. SIA Engineer joint 4, that's the one. Apply. And I got it. So now I just show you to cut time, unselect all the combinations and let calculate just one. And this is how you can do more joints. And now imagine you have some complex design of a joint with, let's say, 20 operations that you would have to click and set every time you would like to co-check the joint within a project or a similar project. It doesn't have to be just this one in this concrete one in the SIA Engineer. It can be any other. This template stays with your IDEA Statica software, not with SIA Engineer software. So yeah, this can help you a lot. So I think that's it. I could continue because I really love this feature of this BIM link, how efficient it is, and what a pleasure it is to work with that. I have more joints here exported to IDEA, the anchoring here as well, and so on. But I will leave that for next time because it's already 11:30. So I will pass the presenter to Reed to comment the weld results. So thanks for now, and I'm passing the presenter.
Thank you very much, Adam, for a really nice example of everyday engineering practice. And we can continue with our webinar. At the start, I want to point out that we will talk about the results of the welds. But at the beginning, I want to show you that we have all things that you may encounter in our frequently asked questions. And if we talk about design and explanation of results of welds, we have here a really nice frequently asked question. How are welds modeled in IDEA Statica? So let's just open it. And we can see on a few examples with a description how are welds modeled, how they are behaving. And for example, and this is really nice one because all of you steel experts are familiar with a typical T-joint welded connection between beam and column without the stiffeners, which is important because then the weld is not acting along the whole length of the weld in the same way. And we will discuss this more in an example. I prepared for you this connection in the IDEA Statica connection application, and we have column and the beam with the same cross-section, HEI 200, and we have only bending moment 50 kilonewton meters. We created connection by cutting the beam and welding it together. And what about the welds? Of course, they are double fillet, but what about the throat thickness? We have two options. First one is that we will type in our desired throat thickness in millimeters, but if we leave here 0 value, then the application will input the value automatically, and the value will be calculated as default value, half of the thickness of the flange or web. So in this case, we have the top flange thickness 10 millimeters. So our automatically calculated throat thickness will be half of that, which is 5 millimeters. And I can see it while pointing at the weld in the 3D scene in the left bottom part of the 3D scene window. Can you see it here? Right here. I will point it on the weld again, and you can read it. Thickness is 5 millimeters, which is a nice feature because you don't need in the first step design your throat thicknesses on each weld manually. You can just leave the 0 there, and if it's necessary, change it later. So let's calculate it. It will be in a second because it's easy connection. And let's continue to the checks with some better explanation. Now I will turn on the plastic strain, and even I have turned the mesh on, which gives me a nice view on the meshed weld. And you can see our weld is created or divided in 8 finite elements. It's a 2D element, and it corresponds with geometry of the weld. It has its own working diagram. It corresponds with the stiffness of the weld, etc. And this finite element is also evaluated. It's evaluated here in the tab for the description of the results. So if I click in 3D scene on this weld, it's get highlighted in the tab, and I can explore it even more. So here, by clicking on the plus, I can see the formulas and values which are used for the code check by code procedures, which is interesting because I can calculate it on my own and just for control, or I can see what's happening inside. And what else do we have here? We have here, which is most important, length of the weld, throat thickness of the weld, the critical load effect, which is code checked, and lots of values of stresses according to the code. The last two are the most interesting ones. UT, stress utilization. And you can see I have here 98 and almost 0.5%, which is quite a lot. It's almost at the limit. But there is a but. You can see that we are, or here is 8 finite elements, and every single element is colored. And these ones are red, and this one is blue, and these are gray. They are not utilized much. And this one, 98.544, is only for the maximum here the maximum element which is utilized the maximum from all of them, the middle ones. But the UTC is capacity of the whole world, so the capacity of all 8 finite elements. This one, this one, this one, etc. And it's some capacity which are calculated by the integration of the area of the limit. And I will show you how it's calculated. Just give me a second. I prepared in advance for you this picture. It's the same connection, but in just a little bit different view. And I just marked here the world. And the world is here, all the data, you can see the same result. And here is the design data for our material, chosen material. Here is the diagram. We have here a stress value for every single finite element. This is the maximum and this is the minimum. And how it's calculated the UTC and what this diagram will show us. This is the blue one, this is the blue part, and the maximum is 428.5 megapascals in the maximum finite element. And this area, this blue area, I will call it area A1. And this green rectangular has a limit 435.6, which is calculated here. It's called limit value. We can call this area a total, as a total capacity of whole world. And if I calculate the values like this, it will give me an usage of one finite element or for a complete world. And you can see here, which is interesting, that in this scenario, we not designed the connection or the world in a good way, because we are using or the world is utilized only in a small area. But from my point of view, I want to design the connection in a way that the world will be utilized for in a whole length. So for me, the information is get back to your design and insert, for example, stiffener here, so the flange will not deformate, it will be more stiffer, and then probably the blue level of the stress will be more equal along the length of the weld. Okay, great. And that's the last thing that I wanted to show you. And I hope it will help you to design your welds in a better way. So I will pass the word back to Adam, and he will finish with the webinar. So Adam, it's up to you.
Thanks, Reed. That was really explaining the whole thing behind the welds. I hope you learned as much as I did. And if I jump back to the presentation, just last things. After the webinar, I ask you kindly to fill a short survey, just 3 simple questions. If you like the recording of this webinar, if you didn't catch all of that, will be till tomorrow or this week on our webpage and on our YouTube channel, so you can watch it again or share it with your colleagues. And of course, if you got interested and you haven't used or installed IDEA on your computer, you can get the free trial version at our homepage, ideastudyguide.com. You just apply on the form and you get it immediately. So don't hesitate if you don't have it, try it out. And not to forget to visit our resource center. If you want to learn more, you can watch the past recorded webinars, past Connection Wednesdays, or other feature webinars that we've done. Everything is on our YouTube channel and web pages as well, so you can browse them. And the last but not least, looking forward to meet you here again in 2 weeks, or actually it's not me that's going to be here, but our colleagues from the UK office from London, Theodore and Kostis, and they will show you very interesting example of a project of a London, very big steel hall. I just forgot the name. And of course, design of a joint in there, and very nice help desk highlight about packing plates. It's already hanging on our website, so you can just join the webinar or sign for the webinar directly if you like. So that's in 2 weeks. So I will see you actually in a month on the next Connection Wednesdays after this one. So I hope you enjoyed it today, and wish you a nice rest of the day, and bye-bye.